everyone. Welcome to another class of fundamentals of particle and fluid solid processing. In the last class we ended with a problem where we have seen that how to use this concept of Stokes law in determining either the terminal velocity or the diameter of this particle. We will be continuing that. So this was the problem that we solved, and let me quickly go through again. So the question was, what was the maximum size of particle as a function of its density for gravity separation or the gravity sedimentation in Stokes law regime. We had to plot its highest diameter possible over the range of a diameter in when it tries to settle in water as well as in air. Okay. And the consideration was that the particles are assumed to be of spherical shape. So the thing we solved, the point here to be noted is that again let me remind you that the critical Reynolds number where until that Stokes law is valid is the particle Reynolds number has to be less than equals to 0.3. So that is the critical Reynolds number in such cases. So we have to equate the Reynolds number of this unknown diameter of the particle with 0.3. By doing so, also the assumption is that this particle, whatever the size is, it quickly attains its terminal velocity. So the acceleration and the time travels to reach that terminal velocity is comparatively lesser. So we can write this terminal velocity expression from this, and this terminal velocity we replace here in this expression, and we find expression of the maximum diameter. Now here for water and for air we replace this rho f one by one by rho f and the mu to get the expressions for, let us say, the air. This is the expression where rho f is 1.2, and in this case rho p is directly mentioned as 1000. So from both this expression we can plot the graph of x versus rho p. The rho p range that has been asked was 2 to 8000. So starting from 2 to 8000 for each and every rho p, or at intermediate or equal interval we can find out what is the x max to find its profile. The profile looks like something like this in water, and the other one is for the air. The reason is there is a rising particle and falling particle curve, because the density of water is 1000, that has been mentioned here, 1000 kg per meter cube, but here if the particle density, the range that has been asked is the 2 to 8000. So that means till the 1000 kg per meter cube range the particle will not settle, it will rather rise. Okay, this is the lighter particle, lighter than the water. So that is why until this 1000 you get a rising particle curve, and then after 1000 you get this falling particle curve, which is similar in trend as of the air but differs in the magnitude. Okay. So this was the last problem that we solved. Now we go to another problem. Here it is asked that a sphere of known diameter and density falls under gravity at terminal conditions through a liquid of known density in a tube of diameter 12 millimeter. Okay. The measured terminal velocity of the particle is 1.6 millimeter per second. So what is the viscosity of the fluid? Okay. So this is a typical problem when we had to determine viscosity of a fluid by falling sphere method. Okay. So the question here that we have a sphere of comparable size to the tube, Now you can notice that this diameter of the sphere is 10 millimeter. The diameter of the tube is 12 millimeter. So it is comparable in the magnitude, which means when it falls through the test tube, it will have its motion or its terminal velocity will be influenced by the solid boundaries. So here that means by mentioning these two dimension, it is indirectly in this problem statement it is mentioned that there is a effect of boundary on the terminal velocity. This you have to understand, because there is nowhere it is directly written that consider the effect of wall. Okay. But by looking at the magnitude of the particle or the object and the container, you can understand that there will be, it is not basically a infinite extent of fluid or the liquid here. Okay. So the spherical object diameter is given, the density is also given. It falls in a liquid which has a rho of 900 kg per meter cube. Okay. The measured terminal velocity, see that term that is mentioned, it is the measured terminal velocity. Okay. It is not the terminal velocity at a free falling condition in an infinite pool of liquid. Okay. So we have to calculate the viscosity of the fluid. Fine. So how do we attack the problem? So the point is this concept I have told you that at first we have to find out from the relation of either the previous two correlations that I showed you, either by Francis or by other correlation, that what is the free fall terminal velocity in an infinite pool of liquid for such spherical particle. If we can find out that, then what will happen, we can apply the Stokes law, okay, and we can find out that what is the viscosity of the fluid. Okay. So the point here, by applying this Francis wall factor expression, because here x by d you can see is near about 0.833, which is lesser than 0.7, that was the limit for applying Francis wall factor expression, and which is nothing but such expression was there, that ut infinite is the free fall terminal velocity in an infinite pool of liquid or a fluid of infinite extent, and this is the measured terminal velocity. Okay. 1 by x minus 1 minus x by d to the power 2.25. This was the expression that I showed you earlier. Okay. So using this expression, what we can find out, because this utd is already mentioned here, x by d we know, so we can find out that what is the ut infinity. Okay. So ut infinity is basically 0.09 meter per second. Okay. If we replace the numerics here, we get this factor as 56.34 multiplied by this utd, which is of 1.6 millimeter per second. We have to convert this to meter per second and then multiply it to get the unit as meter per second. Okay. So that means by this step we have calculated the free fall velocity or the terminal velocity in an infinite pool of liquid. Okay. Now in the Stokes regime, okay, what is that expression for the terminal velocity? We know that, okay, it is the x square multiplied by the relative density multiplied by g divided by 18 mu. Okay. So here this is the particle diameter converted to meter, this is the particle density minus fluid density multiplied by g divided by 18 mu. This is nothing but this terminal velocity in free falling. The thing you have to remember, that the ut that we mention in Stokes law is the terminal velocity in infinite pool of liquid when there is no influence of the side wall or the solid boundaries. If we have to apply, or if you have assumed that the Stokes law is valid, then these things have to be consistent. So that is why to get the u terminal, the terminal velocity in infinite pool of liquid, we had to come through the correction factor of this measured value. So we measured the actual velocity, okay, actual terminal velocity. We have to correct that for the infinite pool of liquid, and then we use it in the terminal velocity expression, equate that with that value, and we get our unknown factor, which is the mu. In this case, the value comes out to be 4.11 Pascal second. So I hope this is clear. Again, the problem statement was a spherical object falling through a tube of known diameter, where the tube and the particle has comparable dimension. Okay, we have a measured value of the terminal velocity. So what is the viscosity of the fluid? So since the dimensions of the falling object and the fluid container is of the similar magnitude, okay, we had to modify, or we had to correct the measured value by a factor, the wall factor, the influencing factor for infinite pool of liquid. Okay, once we convert that, we apply, we assume the Stokes law is valid, okay, and then in the Stokes law regime we apply that expression and do this calculation. But the point is, we have assumed that this is the Stokes law is valid, so we have to verify that statement. Okay, so once we have calculated the mu, we put back in the Reynolds number expression, or the particle Reynolds number expression, because here x is known, rho f is known, ut is known, and the mu. Okay, once we have it here, we see that this value is indeed less than 0.3. So which means our assumption, or when we assume that it is happening in the Stokes law regime, that assumption is justified or valid. So this verification is an important step. We calculate this one, and then we check the Reynolds number is not valid, or not within the range of applicability of Stokes law, then there is something wrong, and we have to use a different expression for the terminal velocity, or the Dirac coefficient, and all these parameters. Hope I am clear with this example. If it is, we move on to the other example. Okay, and this is pretty interesting and complex as well, I would say. So pay very good attention to the problem statement and its solution methodology and why it is. So the problem is, there is now a mixture of particle A and B. Okay, both has a size range of 15 to 40 micron. So we have to now show that a complete separation is not possible using water as the liquid, okay, when it is separated in a rising stream of liquid. So a mixture of two spherical materials A and B is to be separated using a rising stream of liquid. Both has size range of 15 to 40 micron. We have to show that if we use water at ambient condition, it is not possible to separate material A and B. Both this A and B material has their density we have their densities known. A is having 77,000 kg per meter cube, and B is the lighter one, 24,000 kg per meter cube. So this is the first problem, the first part. The second part is that which fluid property then we have to change to achieve complete separation of this material A and material B. Complete separation of, because this is sometimes desired, that we have a mixture of particles A and B, both has identical size range. You want to separate material A from material B. Okay. Now this problem is happening here when there is a rising stream of liquid, and we have to show that if we use water as this liquid, rising water, this separation is not feasible. Okay. So how do we solve such problem, or what should be the methodology, or what has been asked indirectly? The point is that here we have to apply again this terminal velocity concept. Now there is a rising water or liquid, okay, and the particles are settling down. Okay. So if the terminal velocity of the particle are lower than this rising liquid, then what will happen? This liquid will carry out this particles, or carry these particles away. Okay. If that is higher, then this relative velocity is will try to settle this particle. Fine. So schematically, if we understand this problem, that at first think of in a single particle manner. Okay. For single particle, let us say this is the rising stream of liquid, okay, at a velocity u. The single particle, after attaining its steady state, this terminal velocity, if this terminal velocity is larger than the this water stream or the fluid stream, rising stream, then it will settle. Okay. If you further increase the fluid velocity, there will be a point where the fluid velocity is equals to the terminal velocity, and in that case the particle will be a stagnant point, it will not move. And if this rising stream velocity, if it is higher than the terminal velocity, it will go with the liquid. Now the scenario is complex when there are multiple particles. So here what has been asked, that let us say we have two different particles of two different densities. So quite obviously there will be different terminal velocity, there will be a range of terminal velocities depending on the size as well as the density. Okay. So here the similar scenario, let us say the two extremes are this ut1 and ut2, and the fluid velocity is lower than both of them, then what will happen? All the particle will settle. Okay. In other scenario, when this ut1 is greater than u, but the terminal velocity of the other material is lower than that, okay, then one material will go away, one material will come down. Or since this terminal velocity depends on the size as well, because size is the prominent factor, is the terminal velocity varies in square of the size, if you remember the expression. So as the size increases, the terminal velocity will increase. We have seen this in numbers as well. Okay. So in this case, few particles will go away, few particles will come based on this terminal velocity range. And if this rising stream velocity is very high, it will carry away all the material from this region. Okay. So for complete separation, what do we need? We need a critical value of the fluid parameter, that this overlap of this terminal velocity will not be there. There will be a clear separation of the terminal velocity range. Okay. And if that happens, then one material can clearly be separated from the other. For example, let us say if the terminal velocity, there is a clear gap between material A and B, that let us say from ut1 to ut2 is the terminal velocity range of particle A for size range of 15 to 40 micron, and from 15 to 40 micron of material B, the terminal velocity are u prime T1 and u prime T2, and if there is the gap between the T1 UT1 and u prime T1, then what will happen, this material will settle in a different times, and you will have time to separate this material when it is settling. Or it can happen that the other materials are carried out and the bigger particles are settled. So the point is, the bottom line is that we must avoid the overlap of terminal velocity range, since there is a range of particle size and two different density. So we have to think of the two extremes. Okay, so there is heavier material, there is lighter material. Heavier material is A, lighter material is B. Okay, so the heavier material and the smallest size, okay, and the lighter material with the bigger size. Okay, if these two terminal velocities are clearly separated, then automatically all these two materials, the whole range can be easily separated, because you think of that already this heavier material with larger size will have the highest terminal velocity. Okay, lower material, okay, or the lighter material and the smallest size, okay, will have the lowest terminal velocity. There will be significant gap, but at this other end these two overlaps shouldn't happen. Okay, so what I am trying to say is that for complete separation, it is desired that no overlap between the range of terminal velocity should be there. If we can attain that, then it is possible to separate by water, and that means we have to calculate these UT values for these extremes, or the four conditions at least, that is the heavier material A for 15 micron and for 40 micron, for material B 15 micron and 40 micron, and we should check these UT values, and we have to check whether there is overlap or not. If there are overlaps, then the complete separation is never possible. If there is no overlap, complete separation is possible. So that actually answers the first part. Okay, so that means the bottom line is that we have to calculate the UT values by assuming at first that the Stokes law applies. The fluid density, we assume that of water, this is the water that is mentioned, that we have to show that this water is by using water it is not possible to separate. So for water, these are the typical values at ambient condition, that the 1000 kg per meter cube is the density and 0.001 Pascal second is the viscosity. Using these two values, we use it in the UT expression. Again, UT expression is that x square multiplied by the relative density multiplied by g divided by 18 mu. In this case, mu rho f is known as well as g is always known. By doing that, we see that 545 x square multiplied by the rho p and 1000 is the expression. It is written in rho p because we have two materials here, and this is applicable now for both the material. So now if we see that the size ranges, we have 15 micron and 40 micron. Okay, material A, material B. Okay, so for this is material A and this is material B. Material A contains both 15 micron, the lowest one, and the highest one is the 40 micron. Material B, the lowest one is 15 micron, the highest one is the 40 micron, and these are their terminal value that comes from this expression. That we replace this with x is 15 with 15 micron and rho p as it is 7000, yes, 7700. Okay, so we get this value, and then we use x as 40 micron and 7700, we get this value. Similarly, for x is 15 and b we have value of 2400, we use this expression and we get the value 0.17. Again x is 40 and 2700, we get this expression. Now if we look this at this point and very carefully, you will see that there is the overlap of the terminal values, that for material A it starts from 0.28 to 5.84, okay, and UTB 0.17 to 1.24. So there is a overlap of these three values. This UT for the small particle comes in between this thing, which means this 15 micron particle will come with the material B, okay, and the complete separation of this A and B will not be possible since there is overlap. Okay, so I hope you got this point, that here 15 micron of heavier material will fall in between these two extreme of material B. So complete separation by air water is not possible. So what is the influencing factor? The influencing factor here are two, because your this relative density, one is the relative density, the particle densities are fixed. So basically you can change the fluid or the liquid. If you change that, the mu also changes. So which one you should change at first? If you look at it, this terminal velocity is inversely proportional to mu. Okay, so if you change only mu, okay, it will similarly influence both the particles. Okay, but if you change the rho, it will not similarly influence, it will have a different effect. So the influencing factor is basically in this case the density of the fluid. Fine, even if you can keep the similar viscosity, if you change the density somehow of water, you can possibly achieve, but then how much you have to change, that is the question in the next part. So the critical condition is the smallest A, which is the heavier material, will have a terminal velocity is the largest particle size. That is the point that I have mentioned, because these two extreme, these 2 points can have the overlap. Okay, and if this is the minimum or the condition you can avoid, okay, then the complete separation is possible. So by equating these two terminal value, okay, we can understand, we can determine that what is the density that is minimum required to have this value. If we go beyond this, this will be separating, and that is here. If we write these expressions again in this way, so this is the 15 micron square and this is the 14 micron square. Okay, here the material B, here the material A, we find out what is rho, and this is the minimum fluid density that is required to have the same terminal velocity of the heavier smallest one and the lighter largest one. We increase that, these two get separated, we increase that, these two values are different. So we do not have the overlap and we can separate material A and material B completely. I hope this example helps you now to understand the influence or the effect of the terminal velocity, and we will be seeing you in the next class with the other problems. Thank you for your attention.